Hi, this is the last part of chapter 27. Now, this is talking about limits of resolution. Like if we compare, different, let's say, creatures, they have different limits for resolution. And why is that? Because these limitations that they are really created by light. If we look here at this figure 27, we're gonna find that we have monochromatic light. Monochromatic light means light that has only one wavelength, pass through a small circular aperture, and it will, of course, produce diffraction patterns. If you look here, now when we have two sources, they are close to one another. They produce overlapping images because of the diffraction here. This is the one. And if they are close together, they cannot be resolved or distinguished. We're gonna see like about these kind of limitations created by Rayleigh criterion. And here is put in limitation on how we are able to differentiate between 2-point sources. Or like, whenever you have, let's say, a car that is coming from very far, and you have the two headlights, when it's very far, you will not be able to differentiate between them. Okay. Now, what's the limitation is for the diffraction limit to resolution states that the two images are just resolvable, that you can distinguish between them when the center of the diffraction pattern of one is directly over the first minimum of the diffraction of the other. And in order to satisfy this, theta is going to be equal to 1.22 lambda over d. Of course, here again, our theta is really very small. And when it is very small, we know that sine theta equals theta. Lambda, it is the wavelength in meters, and d is the diameter of the aperture or the opening of the lens or a mirror. Diameter. Theta should be in radians. Here, look at this example. The primary mirror of the orbiting Hubble Space Telescope has a diameter of 2.4 meters. Being in orbit, the telescope avoids the degrading effects of atmosphere distortion on its resolution. What is the angle between the two just reversible point light sources, perhaps two stars? Assume an average light wavelength of 550 nanometers. B, if the two stars are at the 2 million light year distance of the Andromeda galaxy, how close together can they still be resolved? The diameter is 2.40 meters, and theta is 1.22 lambda over d. And we can actually say that 1.22 times the wavelength should be converted into meters. 550 10 to the negative 9 divided by 2.4, and therefore they should be the theta should be 2.8 10 to the negative 7 radians. In order for us to find what is the distance between them, we use the relation for the arc length equal the radius times theta, and that is 2 10 to the 6 light years times 2.80 10 to the negative 7 radians. This is going to be 0.56 light years. Now, another thing that is related to light optics is the thin film interference. And that thin interference examples is when you see, let's say, oil covering a wet pavement, and you see these colors of, rainbow, or the soap bubbles. When you're gonna look at it, you're gonna see like different colors. That happens because when the light is gonna be incident on a surface. Okay, one of the lights, one like part of it is gonna go through the medium and is gonna reflect from the second interface, and the first one is gonna reflect from the first interface. This is called like the first interface. Interface means the boundary between two media, and this is the second interface. Now here we're gonna find that we're gonna have two lights that they are really reflected, and based on the phase angle between them, we're gonna have either I would say interference that is constructive or destructive. Now, something that we need to know, that when light reflects from a medium having an index of refraction greater than that of the medium in which it is traveling, a 180 phase shift or lambda over 2 shift occurs. Then here, first thing you need to identify if you have a phase shift for both lights or for one of them only, or one of them or both of them, or it depends. For example, here, if we look at the soap bubbles, we're gonna find that the light is gonna go through air first, and then water, and then air. When it's gonna go from n equals the index of refraction of the first medium is 1 to the second one, which is 1.33, then it's gonna go from low to high index of refraction. Therefore, it's gonna be a phase difference of 180. And when it's gonna go for the second reflection from n2 equals 1.33 to n3 equals 1, there will be no phase. Then there is a total phase of 180. When there is a total phase of 180, the constructive interference occurs at 2 times Tc, which is lambda n over 2 or 3 lambda n over 2 or multiples of these. And the first one is going to happen at this condition. Okay, and for the destructive, is going to occur when 2 dc equal lambda n, 2 lambda n, 3 lambda n, and go on. Okay, and that is really another case that we will talk about. Now, for lens coating, we know that the coating having like about an index of refraction of 1.35, and is gonna be the light is gonna the three media that is gonna go from air to the coating to the glass. Now here, going from the first interface from low to high, then there is 180. And this one from, again, if you compare 1.38 is less than 1.5, then the second is going to be from low to high, and therefore there is going to be an 180 phase difference. Therefore, the overall phase is 0 because both of them, they're going to have a difference. Now then we're going to reverse the cases. For constructive, we're going to have the multiples of lambdas, and for the destructive, interference is going to occur at 2t equal half lambdas and multiple. Let's solve this one here. What are the three smallest thicknesses of a soap bubble that produce constructive interference for red light with a wavelength of 650 nanometer. The index of refraction of soap is taken to be the same as of water. What are the three smallest thicknesses will give destructive interference? Okay, first we need to determine what are the three media that we are working with. The first one is air, the second one is the soap or the water, and the third one is air. Now from here to here, from low to high, is going to be 180 phase difference. If from high to low, 0, then the overall is going to be 180 or pi over 2. Okay, then the first reflection, having phi here, phi means the phase difference is pi over 2, and for the second it is phi equals 0, and then the overall is going to be pi over 2. Then for the constructive we're going to have the half lambdas, and for destructive we're going to have the multiples of lambda. Now we are looking for the first three thicknesses, then we are looking at this one, this one, this one. Okay, lambda n, it is lambda over n2, which is the medium of the thin film. Then we need to calculate that. We choose constructive first. Okay, and then this is the condition for the first one. 2t equals lambda n over 2. And therefore, the first thickness is going to be the wavelength times 4. It's going to be the 4.88.7, the wavelength, divided by 4, and that is going to be 122 nanometer. For the second thickness, this is the condition. 2t equals 3 over 2 lambda n, and then we're going to calculate the thickness, and for the third thickness it is 610 nanometers. Sophisticated cameras use a series of several lenses. Light can reflect from the surfaces of these various lenses and degrade image clarity. To limit these reflection, lenses are coated with a thin layer of magnesium fluoride. This is the glass coating that causes destructive thin film interference. Then when we are going to talk about, the coating for lenses, for sure we are talking about destructive because we want to eliminate the light. What is the thinnest film? That can be if its index of refraction is 1.38, and it is designed to limit the reflection of 550 nanometer light, normally the most intense visible wavelength. Okay, of course, also they give us the index of refraction of glass. Then here I have air coating glass, 1.38, 1.52. Again, you need to decide from air to coating, low to high, pi over 2 or half of a lambda, phase shift, and for that one, the phase shift is 180 or lambda over 2. Okay, and then both of them, they're going to be 180, and therefore we're going to have a phase shift which is 0. Now then, for constructive, we are going to use the multiples of lambda. When we need the thinnest, then we need the first condition, 2t equals lambda n, and because of the coating we need the destructive, and for the destructive this is the first condition. Okay, I need to calculate always lambda n, and then I will use this equation, T equals lambda n over 4, and that is 99.6 nanometers. Now, polarization is the attribute that a wave oscillations have a definite direction relative to the direction of the propagation of the wave. Then, like if we have light, it might oscillate in all the directions. And if it is polarized, I want to maybe have it just oscillate vertical or horizontal, it depends. There is Mala's law that is talking about the intensity of the light after going through a polarizer, and that is I equals I0 cosine squared theta, where I, it is the transmitted wave, and I0 is the intensity of the polarized wave before passing through the filter. What angle is needed between the direction of polarized light and the axis of polarizing filter to reduce its intensity by 90%? Okay, then here I have I equals I0 cosine squared theta. I need to say I over I0 equals cosine squared theta. And then I need to find cosine, which is the square root of this. And I will calculate, because it said it will reduce the intensity by 90, then the remaining is going to be just 0.1, I0 over I0, then the I0s, they're going to cancel, and theta can be calculated as cosine negative 1.3162. Polarizing by reflection. The reflected light, it is completely polarized at an angle, we call it Brewster angle, theta b, and that tan theta can be calculated as n2 divided by n1, where these are the indices of refraction. For example, at one angle, will light traveling in air be completely polarized horizontally when reflected from water? Okay, we know the first medium is air, n equals 1, and n2 equals 1.333. Light completely polarized when reflected. Yeah, it's the first medium is water and the second one is air. Okay, and therefore is gonna be, okay, what did I do? And n2 is 1.33. And theta b at the Brewster angle is tan inverse of negative 1.3133, and that is 53.1. For crown glass, okay, we're gonna repeat the calculation, and theta is gonna be more 56.7. Thank you and have a great day.